Welcome back everyone. So, in this lecture we will see actually some more definitions which will be useful later. So, I will begin with what is called normalizer of a subalgebra. So, let us start with K, so which is a subalgebra of G. So, then the normalizer of K in G is defined to be, so notation this is Ng of K. So, this is those x in G that actually normalizes K. So, that means if you take the bracket x with K, that should be a subset of K. So, this is what we call the normalizer of K in G. Okay. So, now it is not hard to prove, this is again a subalgebra. So, indeed it is the largest subalgebra of G which includes K as an ideal. Okay. So, we will prove that. So, what is our claim or the proportion? If K is a subalgebra of G, so where G is given Lie algebra, so then this Ng of K is again a subalgebra of G. Not only that, this K will be ideal inside this Ng of K, and this is the largest subalgebra that satisfies this property. So, what does it mean? Suppose K is an ideal inside G dash for some subalgebra G dash of G, then we must have this G dash is a subalgebra of Ng of K. Okay. So, these two statements, second statement and the third statement, they are obvious to see. The second statement is just by definition. Okay. So, the way we define the normalizer, that tells if you take any x from Ng of K, then the bracket x k will be subset of K. So, that means K will be ideal inside Ng of K. And similarly, if K is an ideal inside G dash for some subalgebra G dash, then all elements of G dash normalizes K. So, that means G dash will be subalgebra of Ng of K. Okay. So, only non-trivial part is to prove Ng of K is again a subalgebra. So, that will actually follow from Jacobi identity. So, let us check. So, you start with two elements in Ng of K. So, call it x and y, and we want to claim that this bracket x y is again inside Ng of K. So, for that you take any element z inside K. So, we have to verify this x y z is again an element in K. So, this is what we need to prove. So, that means, so we want to claim that this element is inside K. So, let us use Jacobi identity and then rewrite this. So, it is enough to show the opposite is also inside K. Okay. So, that means this is the minus of this. So, then if you use Jacobi identity, this just tells us that this is exactly z x y plus x z y. Okay. So, now note that this x is coming from K, sorry, Ng K. So, that means this z x, this is an element of K. So, this is an element of K. So, now this y is coming from Ng of K. So, that means the bracket, this entire bracket again element of K. So, similarly, you can see that this is also element of K. So, that implies this z x y is an element of K, and that would imply that x y z is an element of K because of skew symmetry. So, that proves the bracket x y will be always element of N G of K. So, that means N G of K is a subalgebra of G. Okay. So, this is just a easy consequence of Jacobi identity, nothing more. So, now we will define what is called centralizer of a subset of G. Okay. So, note that this normalizer one can define it for any subset or any subspace, but the thing is to make it actually somewhat meaningful, okay, one has to start with a subalgebra, otherwise this N G of K will not be even containing K. So, this is the important thing. Okay. So, let us make a note. So, K is subset of N G of K if and only if, so this K must be a subalgebra. Okay. So, that is immediate from definition. So, that is why we are starting with a subalgebra, but otherwise this N G of K makes sense for any K, okay. But in worst case it could be 0. So, that is a problem, and it may not be even a subalgebra. Okay. So, now let us look at another important definition called centralizer. To define centralizer, we can actually start with any subset of G, and then we can talk about the centralizer of that subset. Okay. There is no issue with that. So, what is the centralizer of this subset X inside G? So, this is a set of elements from G such that this actually centralizes this entire X. So, that means it commutes with all elements of X. Okay. So, this is called the centralizer of this capital X inside G. So, again one can prove, okay, it is a easy fact. So, let us check this. This centralizer is always a subalgebra of G, and it is true for any subset X of G. So, let us start with two elements x y in C G of X and then Z in X. So, we need to prove that this bracket x y Z must be 0. So, let us use this Jacobi identity, then we get this is same as first skew symmetric. So, minus Z bracket x y is same as bracket x y comma z. So, then using the Jacobi identity we see that this is same as Z x y minus x Z y. So, now look at this first element, since x is coming from the centralizer of X and Z is coming from capital X. So, this element must be 0. So, that means this whole element will become 0. Similarly, Y is coming from the centralizer of capital X and Z is coming from X. So, this element is 0. So, that means this whole element is 0. So, both the elements are 0. So, that implies this is exactly 0 plus 0, which we wanted 0. So, that means the centralizer of any subset must be a subalgebra. So, we have already seen some centralizers. For example, the center of G is nothing but centralizer of the entire Lie algebra, and we also required centralizers of some particular element. So, for that we just use C G of X instead of C G of bracket X. Okay, this is the centralizer of this given element X. So, this centralizer of some given element will play a bigger role later in theory of semi-simple Lie algebras. Okay. So, we will be actually looking at centralizer of some particular elements called regular elements. So, yeah, when we talk about semi-simple Lie algebras, I will actually emphasize more on this centralizer of regular elements. So, now we have another definition. So, we want to call a subalgebra self normalizing if the subalgebra is equal to the normalizer of that subalgebra. Okay. You start with the subalgebra of G. So, this is called self normalizing if K is equal to N G of K. So, K is always contained in N G of K if K is subalgebra. If it is equal, then again it will be called self normalizing. Again self normalizing subalgebras will be playing crucial roles in the theory of semi-simple Lie algebras. So, we will come to that later. So, now I want to actually talk about automorphism of some arbitrary Lie algebras. Okay. So, these automorphisms are actually very important objects. So, we have to understand them very well. So, let us define and then see some examples of automorphism of G. So, what is an automorphism? Automorphism of G is an isomorphism of G onto itself. Okay. So, if you have a map from G to G which is an automorphism if phi is an isomorphism. Okay. So, in this category, so phi must be linear and Lie algebra homomorphism plus it should be bijective. Okay. And then if we take this automorphism of G, that is the set of all automorphism of G. So, then under the composition it will form a group. So, this group we denote it by automorphism of G. So, this is the group of all automorphism of G. So, we will actually define a particular subgroup of this automorphism of G, which will play actually very important role in the theory of semi-simple Lie algebras. So, that will be called inner automorphism of G. So, we will come to that in a minute, but let us see some examples of this automorphism of G when G is actually linear Lie subalgebra. Okay. So, let us take G to be sitting inside GLV for some vector space V. Okay. So, this is a general linear Lie algebra. So, that means as a set it is a endomorphism of V and then it is an associative algebra with respect to composition. So, you make into Lie algebra, then we get general linear Lie algebra. So, now once we have this information, G is a subalgebra of this general linear Lie algebra. So, then the algebra structure on this endomorphism of V helps us to actually create lots of interesting Lie algebra automorphism of G. For example, what we can do, you start with some x inside this GLV. Okay. So, let us say that is actually invertible. Okay. Let us use different notation. For invertible linear operator on capital V, we use capital GLV. Okay. So, this is the group of invertible linear operators on V, okay, acting on. So, now given this x in GLV, so that is satisfying the following property. So, when you take conjugation with this G, that given G x G G inverse, if it is equal to G, so then we will be able to define the following automorphism on G. So, call that is phi x, so which is a map from G to G given by conjugation. Okay. So, Z goes to x Z x inverse. So, this is clearly invertible linear map from G to G. So, I will leave it to you to check. So, this is not hard to check. So, phi x is invertible linear map. So, the only thing need to be checked is phi x is actually a Lie algebra homomorphism. Note that G is a linear Lie subalgebra. So, that means the product commutator bracket is given by the Lie product is given by the commutator bracket. So, we need to check for any y z in G, this phi x bracket y z should be equal to phi x y comma phi x z. Okay. This is the thing we need to check phi x is a Lie algebra homomorphism. So, now let us go with the definition and then see what is phi x of y z. So, that is nothing but x y z x inverse, but what is bracket y z? That is nothing but y z minus z y. So, that means you can just bring it inside and then complete this calculation. So, this will give you exactly x y z x inverse minus x z y x inverse, but by multiplying x inverse x in between. So, you can get that x y x inverse times x z x inverse will be the same as the first term. The second term will be x z x inverse and then x y x inverse. So, that means phi x bracket y z is equal to the bracket of x y x inverse and x z x inverse. So, which is nothing but phi x y and phi x z bracket. Okay. So, this proves phi x is a Lie algebra homomorphism. Since it is given by conjugation, so it is invertible linear map, that is easy to check. So, that indeed produces automorphism on G. Okay. So, this is a very important way to produce automorphism on G. Okay. There are many interesting automorphisms on G comes from this conjugation. For example, if we start with G equal to GLV, then obviously the condition that we have x g x inverse equal to G is satisfied. Okay. So, x g x inverse equal to G is satisfied. Similarly, you can also take it to be SLV. So, SLV is the traceless operators on V. So, since trace of some x z x inverse will be same as trace of z. So, we can see that x g x inverse will be equal to G even in this case. So, at least for these two examples, this condition is immediately satisfied. Later we will see for some classical Lie algebras. Okay. Again there are appropriate this x that one can choose, so that this condition will be satisfied. Okay. So, this is somewhat gives us a way to construct lots of automorphism from the information that G is embedded inside GLV. But what if we actually deal with abstract Lie algebra? Okay. So, again we are interested in producing lots of automorphisms. So, because these automorphism will be actually later used on act on some subalgebras. So, that you want some kind of uniqueness results and so on. Okay. So, that is why we want to produce lots of these automorphisms. So, we also need to understand how to produce these automorphisms even for some abstract Lie algebras. So, for that we introduce what is called this inner automorphism. Okay. So, let us start with x in G. So, now G is just a Lie algebra, okay, over C. So, nothing special about G, this is just an arbitrary Lie algebra over C. So, now let x be element in G such that this add x is nilpotent. So, since add x is an element of this endomorphism of G, so we can talk about nilpotency of that operator. So, you just assume this is nilpotent. So, say this add x power some k is 0. Okay. So, this is the assumption that we are making. So, then how one can use these nilpotent operators to create automorphisms. So, what we can do, we can use this exponential method. We can simply take exponential of add x. So, which makes sense because we have started with this nilpotent operators. So, which is by definition 1 plus add x. So, 1 means identity element plus add x square divided by 2 factorial plus etcetera plus add x power k minus 1 divided by k minus 1 factorial. Note that add x power k is 0. So, that will imply add x power any r will be 0 as long as r is at least k. So, in particularly exponential add x can be defined. Okay. So, we claim this is indeed an automorphism. Okay. So, this is the claim that we are going to make. Our claim is exponential of add x is indeed an automorphism of G. Okay. So, which will be called inner automorphism. Okay. Indeed, so we take a subgroup generated by this kind of elements. So, that will be called, all those elements in that subgroup will be called inner automorphisms. But anyway, so this can be done in more general setting. So, let us do that way because the computation will be very clear. So, more generally what one can do, one can start with the derivation of G. So, note that add x lies inside the derivations of G. Okay. So, that we have already verified. So, you take some derivation which is nilpotent, again assume delta k is 0. Okay. So, let us say this is the given data more generally. So, now what we do, we use this data to actually create automorphism. As before, we just take exponential of delta and then see whether it is the required automorphism or not. Okay. So, we have already verified, at least I left it as exercise, I think the Leibniz rule for this delta. Okay. Let us recall, if you assume delta power k is 0, okay, then you can see that this delta being derivation will already tell you how to compute this delta power m on this bracket x y. Okay. So, I will leave it to you to check. Okay. So, this is not that hard to check, this is again a Leibniz rule written in a different form. So, if you apply delta power m for any m on this bracket x y, so if you divide by this m factorial, so then what you get is nothing but summation I range from 0 to m, first 1 by I factorial and then 1 divided by n minus I factorial. This corresponds to that m choose I, sorry, let us not mix the notation. So, this is m. So, then you get delta I x bracket delta m minus I y. Okay. So, this is just a Leibniz rule, written it for the Lie product. Using delta derivation one can check this. So, now if we use this and then try to compute what is happening to the exponential delta, so we will get the required thing. So, let us see what is exponential delta. So, exponential delta by definition summation delta power I divided by I factorial, where I ranging from 0 to k minus 1. So, I have assumed, note that delta power k is 0. So, now what we want to claim, we want to climb delta exponential delta is an automorphism of G. So, for that we need to climb exponential delta is actually invertible linear operator and it is also a Lie homomorphism. So, I will leave it to you to check it is a linear operator because combination of linear operators. So, it is linear operator. So, now let us compute what happens if you take the bracket exponential of delta x comma exponential delta y. So, let us compute this. So, then this is exactly equal to, so I just trying to expand exponential delta of x. So, which is going to be summation I range from 0 to k minus 1 delta I x divided by I factorial, and then on the other side delta again j y divided by j factorial, j range from 0 to k minus 1. So, this is the element that we get. If we again try to expand this, so then it will be easy to see. This is will go from, now I can actually increase the index, there is no issue. So, because delta power r will be 0 whenever r greater than or equal to k. So, that means I can go from 0 to 2 k minus 2, it will be clear why I want to do that. So, then this will become exactly equal to summation this summation I range from 0 to, let us change some indices. This is n from 0 to 2 k minus 2 and then where I ranging from 0 to n. So, that this will become delta I x divided by I factorial and then delta n minus I y divided by n minus I factorial. Okay. So, this is what we get. So, now if you use Leibniz rule, you can see that, so this is the element, okay. So, that is there for the Leibniz rule, okay. So, this is that element. So, one can replace this by the following summation n equal to 0 to 2 k minus 2, then this is going to be delta n x y divided by n factorial, because that is what on the left side. So, this is all there on the left side. So, you get which is equal to exponential of delta bracket x y. Okay. So, that proves exponential delta is indeed a Lie algebra homomorphism. So, that is what this checking tells you. Okay, just a simple calculation which I am just doing. So, now it is not easy to it is not hard to write down the inverse. So, what we do, we just write exponential delta to be 1 plus eta. Okay. So, then one can easily check this eta must be again nilpotent. Okay. So, I will do this checking in general for any elements of the some ring. Okay. But let us postpone this. Okay. So, here is the climb, this eta is again nilpotent. So, because this is again nilpotent where inside that endomorphism of G. Okay. So, then what we can do, I can simply write down the formula for this inverse of exponential delta. So, which will be, so let us say eta power some k dash is 0. So, then what is the exponential delta inverse, which is just 1 plus eta inverse. So, by formula this is just identity minus 1 minus eta plus eta square minus eta cube plus etcetera plus or minus eta power k dash minus 1. So, I will leave it to you to check, this is the correct inverse for this exponential delta when you write exponential delta equal to 1 plus eta. So, now let us check what is this eta and then why it is actually nilpotent. So, what is eta? So, if you recall the definition of exponential delta, so which is just summation delta I divided by I factorial. So, that means eta is nothing but delta plus delta square by 2 factorial plus etcetera. Okay. So, what is eta? Eta is delta by 1 factorial, delta square by 2 factorial plus and so on plus delta power k minus 1 by k minus 1 factorial. But the thing is all these elements, individual elements that you see here, they are all commuting elements. Okay. Suppose you have two elements in a ring, let us say R is a ring, not necessarily commutative. You have two elements in a ring such that AB equal to BA, both of them commute, and A power k is 0 and some A power k dash is B power k dash is 0. So, that means both of them are nilpotent. So, then you can prove that A plus B power, some power will be 0, which is exactly you can see that k plus k dash minus 1 will be 0. Okay. So, this is just a direct consequence of binomial expansion. So, if you write A plus B power r is equal to summation or choose I A power I B power r minus I, where I range from 0 to r. So, then you can see that this indices, okay, when r equal to k plus k dash minus 1, that would imply either I is at least k or I dash, okay. So, that is r minus I is at least k dash. Otherwise, what will happen? I will be less than k and r minus will be less than k dash. So, that will imply r less than or equal to k plus k dash minus 2. Okay. So, this will imply this is minus 1, this will imply r minus I less than or equal to k dash minus 1. So, that would imply r is less than or equal to k plus k dash minus 2. So, that means if r is at least k plus k dash minus 1, that would imply I is at least k or I r minus I is at least k dash. So, that will say A plus B power r must be 0, okay, if r is at least k plus k dash minus 1. So, this is now I have done it for 2 elements. Now, it is not hard to generalize this for any k number of elements, all of them commute, okay, and all of them are nilpotent. So, since delta is nilpotent, any power of delta will be nilpotent and powers of delta will commute with each other, that will imply eta will be nilpotent. Okay. So, this way actually we are getting lots of automorphism of G. So, now we can define what is called this inner automorphism of G. Okay. The inner automorphism of G is defined to be the subgroup generated by all these exponential add x, where x is in G such that add x is nilpotent. So, such elements we call it actually add nilpotent elements. Okay. So, an element x in G, so let me write it properly, an element x in G is said to be add nilpotent if add x is nilpotent. Okay. So, in that language, so you are taking subgroup generated by exponential of add x for all add nilpotent elements x. So, this is actually a subgroup inside automorphism of G. We claim that this is indeed normal subgroup of automorphism of G. Okay. So, this inner automorphisms is indeed normal subgroup of automorphism of G. So, why it is normal? Because one can check it for the generator, that will be enough. So, you start with some pi inside automorphism of G. So, all we need to prove that pi actually, like if you take the conjugate with respect to pi, this inner automorphism of G, then that should be subset of inner automorphism of G. So, that means you start with an element in automorphism of G and some this element in inner automorphism of G, which will be a product of this exponential of add x. So, it is enough to do it only for the generator. So, you just take this exponential add x inside inner automorphism of G. So, where this x is add nilpotent. Okay. So, then what do you need to prove? You need to prove that pi exponential add x pi inverse should be again inside inner automorphism of G. But this just follows from the following calculation. Okay. One can easily check. So, this pi exponential add x pi inverse is nothing but exponential add pi of x. Okay. So, I will leave it to you to check this is the case, and then if x is odd nilpotent, then pi of x also will be odd nilpotent. Okay, that is also something easy to check. So, that will imply that this is inside again inner automorphism of G. Okay. So, this can be just verified using the following. So, what one can do, you just do this pi add x pi inverse, and then you can see that this is nothing but just add pi of x. Okay. So, first to verify this. So, just to verify this and then use this to verify this. Okay. So, this is that something I am leaving to you to check. So, now let us see some example. Okay. So, we start with this SL2C. So, which is actually a subalgebra of GL2C. So, indeed it is linearly subalgebra. So, we already have this nice basis for this SL2C, which we denoted by x, h and y. Okay. Recall x is nothing but 0 1 0 0 and then h is nothing but 1 0 0 minus 1 and then y is nothing but 0 1 0 0. As an elements of this M2 of C, this x and y are both are nilpotent. Okay. These two are nilpotent. So, now that means we will be able to actually create some automorphisms as we discussed. Okay. For example, what we can do, we can take this S to be exponential of x and then exponential of minus y and then exponential of x. Okay. So, this will be automorphism of this C2. Okay. So, this is actually invertible element. So, now using this element GL2C, so you can see that SG S inverse will be again G. Okay. This is easy to verify. So, now with this data what we can do, we can actually define this phi S. So, that will actually give us automorphism of G, which is given by the conjugation Z goes to S Z S inverse. So, I actually leave it to you to check. So, this is something one can verify by very explicit computation that phi S of x will be equal to minus y and then phi S of h is nothing but minus h and phi S of y will be minus x. So, this is an automorphism on SL2 that map x 2 minus y, h 2 minus h and y 2 minus x. Okay. So, there is another automorphism again comes from the similar thing. Okay. So, it is again not hard to check. So, if you take this x and then look at add x, so that will be again nilpotent. Okay. So, I will verify this for any arbitrary linear Lie algebra, but anyway let us take this fact for granted. So, what I am saying exponential of add x makes sense as add x is nilpotent. Similarly, add y is also nilpotent. So, in particularly we can talk about this particular element sigma, which is exponential of add x, exponential of add minus y and then exponential of add x again. So, this is some element inside the inner automorphism of G. Okay. So, this is maps G to G as it is an inner automorphism. What one can prove? One can prove that this is same as the earlier map that we constructed phi s on G. Okay. So, this is something I leave it to you to verify. So, this sigma is same as phi s. Okay. So, now let us check why this add x is nilpotent. So, let me do this in much generality. Okay. So, what I want to do? I want to take some linear Lie algebra, okay, Lie subalgebra. So, in that, okay, let us start with that. So, let us say G is linear subalgebra of GLG, sorry GLV. So, now take some x inside G, which is nilpotent. So, that means as an element of GLV, it is nilpotent. So, this is nilpotent operator. Okay. So, now what we claim? We claim that add x, which is a map from G to G, is again nilpotent. Okay. So, how to see this? So, note that what is add x? Add x is nothing but it is now given by bracket x y, but this bracket x y is happening inside this linear Lie subalgebra. So, that means this is a commutator bracket, this is just x y minus y x. So, the best way to think about this add x as sum of two maps. So, you can define what is called this left multiplication lambda x. So, where lambda x of y is equal to x y, and then this right multiplication rho minus x. So, rho minus x of y to be minus y x. Okay. So, using these two maps, it is easy to see add x is nothing but lambda x plus rho minus x. Now, it is not hard to check lambda x and rho minus x both commutes. Okay. So, let us check. So, if you apply it on some y, then what do you get? You get basically x y minus x. So, which is nothing but minus x y x. But on the other hand, if you apply rho minus x lambda x on y, you get y x again minus x. So, which is equal to minus x y x. So, this proves that you have written add x as two commuting operators. Okay. But note that if x power k is 0, that would imply lambda x power k is also 0. Why? Because lambda x power k applied on y will be just x power k applied on y, okay, which will be 0. Similarly, you can see that minus rho x power k is also 0. So, that says you wrote add x as sum of two nilpotent operators, and they also commute. So, that would imply ADX is nilpotent. Okay. So, this is again goes back to the exercise we did. So, this proves that given any nilpotent element, okay, if you consider the corresponding ADX, thus that must be nilpotent. So, now actually I will end this lecture by some small calculation. So, which actually tells about really what is happening here. So, this exercise indeed helps you to verify the statement sigma equal to phi s. Again this is happening at the level of linear Lie subalgebra. So, just let me just write it here. So, you start with G, which is a linear subalgebra of GLV, and then take x in G, so which is nilpotent. Okay. So, because x is nilpotent, we can write add x as lambda x plus rho minus x. So, we also verified lambda x and rho minus x, they commute. So, in particularly if I take exponential of add x, so how it will look like? It will look like exponential of lambda x plus rho minus x, but the law of exponential will tell whenever these two terms commute lambda x and rho minus x, I will be able to split this exponential into individual product. It will be exponential of lambda x times exponential of rho minus x. So, but what that mean? If you just go back to the definition of lambda x, exponential of lambda x will be lambda exponential of x. Similarly, exponential of rho minus x will be rho exponential of minus x. So, this simple calculation you can use to compute what is really happening for the sigma. Okay. The sigma is given by exponential add x, exponential add minus y times exponential add x. So, you have to apply 3 times, but exponential add x has a very nice formula which is here. So, you can use that and then just compute. So, that calculation I will leave it to you. Okay. I will stop now. I will actually continue my next lecture by defining what is called soluble and nilpotent Lie algebra. We will also see some basic properties of them. Okay. Thank you.